Good morning, everybody, and thanks for inviting me. Do you see the presentation, the slide? It's okay for...
Yes, it's perfect. Thank you.
Okay. So in my presentation, I will give you an overview on some concepts that are necessary to move from risk assessment to resilience assessment. And in particular, the three main concepts I will describe are the systemic thinking, the probabilistic inference, and how this kind of new way of thinking fits perfectly into the resilience engineering concept. Then I will show you some tools to apply this concept in the real situation and in real major accident plans. And I will show you some application cases. So the first concept is related to the systemic view. Traditionally, the engineering approach is systematic because engineers often are decomposing the system in single components and also decomposing again in subsystem and subcomponents in order to very accurately study the components. But this kind of approach is missing an important point of view, which is the interaction between the components of a system. So the new approach to safety and to the resilience engineering is to considering the system as a whole. And that is important because that implies to move our focus from only the components to the interactions among the components, because in this interaction, safety can emerge as an emergent property of the system. The word system is coming from the Greek, which means put together. That means establish a context. And, as already mentioned, exploring the nature of the interdependence. So, the traditional engineering view is characterized by the systematic approach. So, as I told you, independent phenomena, and each component of a system is studied separately. We have to move by catching interconnection, and this word is called resonance. And this how the behavior of a system component is affecting the other component and also the whole system. When I'm talking to emergent property, I refer to something that is not findable in the system components, but is only findable in the interaction. To give you an example, the fluidity of water is not inside the water molecule, but we can experience it when the water is flowing, when forming like a drop, or when we open the tap. So we need integration, but what kind of integration we need? For answering to that question, we have to go through the knowledge, the famous knowledge pyramid. And of course, we have to give meaning to the very large amount of data that are always present in our plants, in our system, in our critical system. But most of the time, we are looking at that data only when something is going wrong. But the real part, the most important part of information inside that data is hidden, because it's hidden when the systems are performing well. So we have to give more meaning to the data and explore that data and the dependencies on data. Putting the data in a context, it means to have information on the system. We can connect the separate part of the system. putting information from a bunch of components inside a complete system means the formation of a wall. And this is the transformation from information to knowledge. And the next step, which is related to catch the interdependencies and also can make prediction and improve the decision-making process inside an organization, is what we can call wisdom. So we have to climb this knowledge pyramid in order, starting from giving some meaning to our data, to reach the wisdom on the entire system. And this reflects in a very practical example, putting into a graph the connectedness of our system and the human understanding. By climbing the pyramid, we reach a deep understanding of the principle, but not only the deterministic one, but also the, let me say, chaotic ones, because the interaction in most of the cases are not expressible in a deterministic way. So we only may have some belief on our structure and on our system is working. Talking on risk, we can start from this very known distinction. Starting from the upper right corner, we have the known risk. These are risks we know about, and we are aware, and we also know how big they are. These kind of risks are the easiest to manage. And this is the field of deduction. Moving left, known unknowns are risks that we are aware of, but it's unsure the size of the effects. We have to plan in managing this kind of context for the most probable outcome. In the same way, unknown known risk are risks that are disregarded inside an organization, intentionally or unintentionally. The management of unknown known risk require a constant monitoring in order to find preventive action. Those kind of risks are the field of induction. Moving in the bottom left corner of the picture, we can find unknown risk that are the most dangerous. There are risks we don't know. We don't know how they can manifest, and we also don't know the size of effects. This kind of risk are the ones that are called the black swan. And in managing this kind of risk, it's the field of abduction. Deduction, induction, and abduction are the three main approaches of inferential reasoning. When we are applying the deductive logic, we are starting from true premises, and our conclusion is guaranteed true. That's why this is the field of known risk. And this is very easy to manage. The inductive logic, for the fact we are unsure of the effects of a risk, we can only make conclusion that it's probably true. But the most difficult case is the abductive logic, because we have a limited set of data. Our knowledge is very limited. So, step by step, our conclusion can only be a best guess. And the conclusion is also subject to some even relevant modification when new evidences are manifest inside our system. And a very powerful tool to deal with this kind of risk and this kind of reasoning, the abductive reasoning, is the bias theorem. Because bias theorem is an expression of our degree of belief, of how we can be certain of our belief. But this kind of certainty in our belief system can be modified by when new evidence are present. So this is the main element of the bias theorem. I don't go deep in the mathematical formulation of the theorem, leaving that maybe for others if some questions are present. But this is the most powerful tool to deal with the black swans. This kind of subdivision into the inferential reasoning can be found also in the risk assessment evolution. The first model for the risk assessment, well, the first notable model for the risk assessment is the domino model. The domino model explains accident as a linear propagation of causes and effects. This model was associated with one of the earliest attempts of formulating a complete theory of safety. According to this model, we can interrupt the chain of causes and effect by making better one of, well, the domino tiles, let me say. But this kind of model, which is very, very useful in the field of deduction reasoning, is not so useful in the other risk management approaches, because reinforce the misunderstanding that accidents have a root cause. And this is not always, let me say, never true. The second risk model is the Swiss cheese model. And according to this model, the accident can be seen as a result of interaction between unsafe acts and some weakness of the barriers we put between the danger and the risk. The structure of the domino model is always a linear structure. We associate some probabilities because we are associating the probabilities of the failure of the barriers in this kind of model. But the misunderstanding is the same of the domino model, because even in the Swiss cheese model, the accident can have a root cause we can luckily eliminate. In this kind of model, we are talking of probability, and that's why this is the model for the inductive reasoning. The real challenge is to recognize that complex systems are non-linear and are dynamic. The real system must be able to adjust the performance according to the very momentary condition that arise. So that's why we need a model that can update the outcome during the operation of a complex system. The term used for describing this non-linear interaction between the system components is concurrence. That's why we need to modify our way of reasoning in order to managing the real risk and the black swans, and to move to the abductive reasoning paradigm. And this is the main reason why traditional quantitative risk assessment often fails. Because in the smallest square in this slide, we can recognize the element of the traditional risk assessment. The fault tree and event tree represented in the bow tie structure are, let me say, the manifestation of the inductive reasoning. But in analyzing real system with this kind of approach, we found issues on data and issues on the model itself, because we are lacking information on the definition of likelihood in fault tree and event tree, but most of all in the definition of interdependencies in fault tree and event tree. This is mainly related to, well, let me say, the static nature of the traditional quantitative risk assessment. For example, we are considering as the basis of the whole process the failure rates, which are most of all taken from the scientific literature or from the operative experience in some cases in the industrial plants. But they are considering like written in the stone. But this is not true, because the failure rate of a component is fluctuating relating to the ongoing operation. That's why we need to move from the quantitative risk assessment to the dynamic risk assessment, and we have to build dynamic model able to define likelihood from priors and posteriors distribution and able to define interdependencies. And the best way to define interdependencies is the Bayesian inference, the Bayes theorem I showed you before. So we are able to express the risk as a probability density function and not only as a probability. This is the main element of the dynamic risk assessment. Some powerful tools for approaching the resilience assessment is given to us from the machine learning, from the artificial intelligence field. We are talking of safety 4.0 because in this kind of concept, artificial intelligence, machine learning, and big data, and with the term big data, I mean what I've told you before, that is giving meaning to our big amount of data. And this concept are putting together for improving the whole risk assessment processes. By analyzing in real time the data coming from the plant, but also coming from the whole system, including the environment, all the stakeholders, the human factors, and so on, by analyzing this data moment by moment, we can dynamize our risk perception and our risk indication. Of course, the heart of the process is the process engineering, because we have to put a lot of expert knowledge in the machine learning models, because when we don't have this step, when we don't put our expert knowledge into the models, let me say that the machine learning models are discovering the hot water, because most of the dependencies a machine learning model can discover are already known by the first principle model. Okay, so the future of safety and the resilient approach to safety must integrate machine learning and artificial intelligence and human intelligence in this kind of system. So we also can use first principle models, but we can update the first principle models with the machine learning outcomes. Of course, for doing this kind of journey, we have to integrate our plans with the real-time sensing system, from which we have to determine the inference on the interaction. So we need the algorithm for the early detection of what? For the early detection of the system weak signals that are the precursor of some probably disruptive events. So putting in the box knowledge, data with meaning, and artificial intelligence, we can reach the goal of the safety 4.0, which is the resilient approach to safety. So we move from some kind of approaches which are mainly rooted in the protection and reaction, because we are focusing on the loss of functionality of our system components. That is like considering the failure already happened, or the prevention, in which we have uncertainties, like in the fault tree model. So this is the representation of consequence-based or risk-based model. From prediction, real-time monitoring system, we have to detect the significant precursors. And we have to move from protection and prevention to a proactive approach, which is the resilient approach based on the real-time condition. And this is the early detection of weak signal I anticipated before. This is the data-driven modeling and the resilience-based approach. This is a quick overview of the resilient principles, main principles, because for resilience engineering, the failure is the result of the adaptation. The adaptation to what? The adaptation to the fluctuation in the performance of the system components. So a resilient system is able to maintain and regain a state of dynamic stability. That's why we can underline the resilience guide words, which are monitor, learn, anticipate, and respond. In order to catch these four very important concepts,
Tomaso, it would be great if you could finish in the next 3-4 minutes.
Okay. I will show you the framework for catching the four resilient guide words, which are mainly rooted in the data-driven models. And from that kind of model, we are able to make prediction on the states of our system. This is how a machine learning model is functioning. We need a learner that is an algorithm that captures the trend and is able to make prediction when properly trained. This is some kind of machine learning. And we are starting from supervised learning because we know the input and the outputs, but we are moving to reinforcement learning because the target of the resilient safety is a system that can adjust itself. I will go quick, not describing how the bias theorem is applied to the failure rate, but what I want to show you is that typically a system failure is a spot inside a behavior of the system that we can consider safe. But this is not true because we always have hidden states, intermediate states between safe and failure. And the formulation of this kind of tool, the hidden Markov model, by integrating the process variables inside the Boolean failure probability, can give us the chance to control dynamically the process and to express risk in a dynamic manner. I will also show a brief result. This is how the whole operative control system can be built. We have to build some models, some dynamic model, machine learning model for all the operations that are going in our system. We have to assess risk for the operation with other machine learning models by predicting these weak signals, integrating all those models with an asset integrity model. And so with different layers which are communicating each other, we can build a dynamic operating control system. This is how we apply this kind of system to a bunkering operation for liquefied natural gas. And we are able to predict the system states in order to catch some failures in the system components. And that's all. Thank you very much.